So, as we have already seen that how the remote sensing and GIS technology is being used in different natural resource management. So, you will be always leaning terms that are very popular in GIS. Those terms are digital elevation model. So, whenever you will find any uh, papers when you're reading through or whenever you're doing any kind of research related to any of the natural resource management, always you have to look for the topography. So the topography is different from different area. If I'm situated in Himachal, if I'm situated in Arunachal, if I'm situated in Jaipur, if I am situated in Gujarat, what is the difference? The difference is topography. The difference is in the height. So the height plays an important role in various natural resource management. So in order to obtain the height about an area, what are the methods or the instrumentation through which you can obtain the height? Either you can go into the field, you can carry some field equipments related to your DGPS, GPS total station, and you can create uh, contours of those area, and then you can create a topographical map. But when it comes to satellite images, we are using the satellite images for creation of the contours of those area in order to have a basic understanding about the topography, slope, elevation, height. So you can feel and you can say that the digital elevation model are very important for any kind of the analysis when you are doing in a remote sensing, whether that is a geostationary purpose, you're going for cyclone analysis using the geostationary data, irrespective of the data sets, whether ever you're talking about the hyperspectral data or microwave data, optical data, whatever data you talk about, but at last you have to apply those data sets on the ground. And in order to have an understanding of the ground, because you are not familiar with each and every place, what is the height, what is the height in Bihar, what of that is specific area, what is the height in Jammu. So in order to know the topography, then only you can do various kinds of analysis, whether that is related to disaster, drought, flood, crop, agriculture, then shifting cultivation, all depends on your topography. That's why digital elevation model is very important for any kind of study when it comes to remote sensing and GIS. So the term digital elevation models describes about the digital imagery of elevations, topography, or bathymetry. It is digital. What does digital means? DMs more often are produced, distributed, and analyzed in soft copy or electronic format. It describes the elevation of the ground surface, exclusive of man-made structures, vegetation, or any other objects above the ground. So whenever you go, you travel in a train, when you pass through any railway station, you will be finding a name, and there will be a uchai. It will be written height. 600 meter above mean sea level, 800-meter above mean sea level. So what are those? Those are the height. Height means elevation. So finally, it is a model in two senses. First is a distal elevation model is a pixel. Obviously, when you are seeing distal elevation, you will be getting a raster data. We are talking about distal elevation model in terms of remote sensing and GIS. We are talking about raster data. So when we are talking about raster data, we are talking about pixels. So a distal elevation model is a pixels based model representation of the earth surface. So what that pixel contains, that pixels contain the information about the topography of that area, When it comes to satellite images, it comes information about the object, but here it contains the information about the height of that area, about the contour of that area, where each pixel of a DM represents an elevation value. So what does that value digital number you have in remote sensing and GIS? Here each pixel will have a value, and that value corresponds to the height of that object. Secondly, computers and algorithms can use a DM as an input to model or analyze the 3D topography. So if you want to have a 3D representation of an area, you want to know the height about the area, you want to see the topography, you want to see the slope, you want to see the aspect, and for that, until unless you don't have a digital elevation model, you cannot generate the slope, you cannot generate the relief map, you cannot generate the shaded relief map, you cannot generate the aspect map. So digital elevation models is a discrete representation of continuous 3D surface. So what does that digital elevation model contains? That contains 3D surfaces that corresponds to each x and y. There is a discrete z values, means for each and every pixels you will have a value, and that corresponds to the z value, that is the height of that object. So you can see that here there is a digital elevation model taken from the Cartoset 1, that is an Indian digital elevation model, and here the white surfaces are the representation of a hilly terrain, means there is a height, and this darker in color, and as you go you can see the drainages, you can see easily identify the drainages. So these are the low lying structures. So when in digital elevation model you see bright white, means that denotes that is a top or the peak, and when you go downwards the dark blue or the dark black, in the form of drainages, you can see these are the lower elevation model. So by seeing a digital elevation model you can identify the height, you can identify the slope. You can see on the left hand side, you can see the different kinds of slope, different kinds of drainage patterns. The drainages can be identified using digital elevation model. So some of the terminologies that we generally talk about or generally we use in the day-to-day exercise in remote sensing GIS or urban planning. One is digital elevation model, where the generic term is for the altitude grid. Then you have got digital terrain model, that is called as DTM. DTM corresponds to ground elevation model. Then you have got a DSM, that is called digital surface model, that is ground plus cover elevation model. And then you have got digital height model, that is said as DHM, that is cover elevation model. So here you can see the difference between a surface model and a terrain model. When you say a digital surface model, means it is also incorporating the canopy cover, means the height of the tree. The height of the tree will also be model when you will be using the DSM model, that is surface model. And when you will be using the DTM, that talks about the terrain, that excludes the canopy cover, whatever height it has, that is excluded. So what is the difference between DM, DSM, DTM and DHM? A digital elevation model is the raster representation of continuous surface. Means that is a continuous surface, like if you go from upwards to downwards, there was a decrease, so means 800 feet, then you will get 700 feet, then 600, then 500, then 400. So that is a continuous surface. Then when you talk about DSM, that is called surface model, it includes buildings, vegetation, roads and natural terrain features. So here you will be knowing about the surfaces also, what is the height of those surfaces. So DSM may be useful for landscape modeling, city modeling, visualization application. So when you talk about surface nowadays, whenever you see a map related to urban a smart city, you will be seeing a 3D map of that area where the height of the different buildings will be shown with different colors, with different shape, with different size. But when we see our digital elevation model, we do not see those surfaces, because each and every application has got different purpose. So if you want to see the height of the buildings, so you have to first create a DSM, and on the basis of DSM you can recreate the real representation of each and every building what is represented on the earth surface, whereas a digital elevation model is used for flood drainage modeling, land use studies, geological applications. So whenever, so you can see that the purpose are different. So depending on your objective of the research, depending on your purpose of the research, you will be selecting whether you will be going for the DSM model or whether you will be going for DEM model. Both the models are available. Then you have got distal terrain model that generally refers to a representation of the earth surface, excluding features such as vegetation, building bridges. So when you talk about the terrain, we are talking about the land surface. We are talking not including the height of the building, not including the height of the trees, not including the different heights of different earth features. So we are talking only about the terrain. So DTM model provides the bare earth model divide of landscape features. So in a real sense, if you want to understand what does DTM provides, so DTM provides you information related to the earth surface, excluding the various landscape feature. When you say about DSM, you have to include each and every earth surface, whether that is a vegetation or whether that is a settlement. So all will be stated in that. So when you're talking about this, DSM minus DTM will be your NDSM. So why distal elevation model is required? Why we use this DMs always for our studies? Because the distal elevation models are the primary data used in the analysis of catchment topography, and DEM are widely used. I have already stated, like in hydrology, you want to see the different drainage patterns. Their ordering has to be done. So manually, if you are doing it, it takes a lot of time. A lot of accuracy is required when you are creating a drainage in any area. But when you use distal elevation model, nearly 80 to 90% of accuracy can be obtained, and the drainages can be extracted automatically from the distal elevation model. So that will save your time, that will save your energy, that will save your lot of work. So if you are going for any infrastructural development, whether that is related to urban 3D CT models, whether you are going for any strategic applications like we have got border countries Pakistan is there, China, Nepal or Bhutan, they're the adjoining countries. So we have to plan accordingly for our military purposes, for our intelligence purposes. For that, you need to have a topography, you need to have a elevation map of those areas so that we can plan accordingly. So for a strategic application, this distal elevation model is very important. Thereafter, glacier mass balance studies, environmental studies, whether you talk about forest fires, whether you talk about biodiversity conservation, whether you talk about habitat suitability, all will require a distal elevation model. Thereafter, large-scale topographical maps will be produced. Then engineering design, whether you want to go for hydro engineering or any kind of engineering purposes, site suitability purposes, you have to include the distal elevation model. Then cut fleet analysis, rural and urban department development programs, whether that is related to Panchayati Raj or any commercial applications that you are using in GIS, will be requiring the distal elevation model. So a specific hydrological application of digital elevation model, it is used for water resources management, hydrological modeling, flow channel characterization, water catchment, watershed mapping, because you have to see the watershed area. So you will be using that digital elevation model to identify the different kinds of watersheds available in your area. Then floodplain characteristics, stormwater management, wetlands mapping, water supply and sanitation, bathymetric analysis, which requires the depth map of any area, flood line management, whether that is flood extent, depth, impact, coastal information. So you can see that a lot of applications are based on your distal elevation model. So whenever you see an earth, when we use in remote sensing, we feel that somebody says is the shape of the earth is spheroid. Some scientists say that the shape of the earth is ellipsoid. But we in remote sensing, when we are taking GPS instrumentation for recording of the data sets, we assume that the earth is geoid. Geoid is an arbitrary surfaces representing the earth surfaces. So this is how the earth look like in case you have taken you feel that the earth is a geoid. So you can see the variation in the shape, the variation in the height, the variation in the depth. So what is the geoid? So geoid describes the irregular shape of the earth, and it is the true zero surface for measuring elevation. Geoid is defined as the particular equipotential gravity surface that coincides with the mean sea level and that may be imagined to extend through the continents. The geoid is that surface to which the oceans would conform over the entire Earth if free to adjust to the combined effect of the Earth mass of attraction and the centrifugal force of the Earth rotation. This is everywhere perpendicular to the force of gravity. Then again, I have already said that many of the scientists assume that the Earth is an ellipsoid. So an ellipsoid is the 3D surface obtained by rotating the ellipse in a major minor axis. So you can see this is the mathematical formula on the basis of which some scientists say that the shape of the Earth is ellipsoid. Then we take datums into consideration whenever you are going for any kind of 3D measurements, 3D projections. So providing a projection to any data requires datum. So what is a datum? A datum is defined by any numerical or geometrical quantity or set of quantities which serve as a reference point from which we measure other quantities. A datum is a mathematical model designed to the best fit part or all geoid. The ellipsoid will fit either globally or locally. The datum is defined by an ellipsoid, and the relationship between the ellipsoid and a point on the topographic surface is established as the origin of the datum. So the geoid surface cannot be directly measured or observed. The heights or below the geoid surface can't be directly measured and are referred by making gravity measurements and modeling the surface mathematically. A geoid is approximated to the mean sea level and used as a reference for measuring height. The geoid is a surface along which the gravity is always equal and to which the direction of gravity is always perpendicular. Uneven distribution of the earth mass makes the geoid surface irregular. Then you have got different kinds of datum. In geodesy, cartography, and navigation, there are two types of datum. Either you say that is a horizontal datum, and the other one is vertical datum. So the horizontal datum forms the basis for the computation of horizontal position. The vertical datum provides the reference to measure the height or the depth. A datum may be classified into global and regional. In global datums, the ellipsoid first fits best globally, and the center of the ellipse coincides with the center of the earth. WGS84 Datum, which is one of the most common popular example, is based on the geodetic reference system of 1980. In regional datums, the ellipsoid best fits regionally, and the center of the ellipsoid is non-geocentric. That is, Indian average datum is a local or a regional datum. So you can see what is the relationship between the ellipsoid and the geoid. See, you see how the terrains look like, what we assume for the ellipsoid, what we assume for the geoid. So the vertical separation between the geoid and a particular reference ellipsoid is called geoid undulation, and the numerical values of the undulation evidently depends on the particular ellipsoid we have used. For a global reference ellipsoid, they can reach up to 100 meters. The geometrical relationship between the geoid undulation and the ellipsoid height h and the orthometric height h is obtained from spirit leveling, and that is small h equal to big plus n. So satellite techniques based on digital elevation model, you will be using the satellite photogrammetry, then Sar Interferometry, radar altimeters, radar grammetry, lidars, all will be making or will be using all these satellite data sets to obtain a digital elevation model, and the remote sensing data generally captures the surface height, so the top of the tree canopy or the building is returned, not the bare ground elevation. So when you talk about satellite photogrammetry, we have already studied in our earlier class what you mean by photogrammetry. So the name photogrammetry is derived from the three words, Greek word, that is photos or foot, which means light, gramma means letter or showing something drawn, and matter or metering is the noun of measures. So the definition of photogrammetry is defined as the art, science, and technology of obtaining reliable information about the physical objects and the environment through the process of recording, measuring, and interpreting photographical image and patterns of recorded radiant electromagnetic energy. So you have got the various kinds of classification of photogrammetry. You can say interpretive photogrammetry that recognizes and identifies an object. Then you have got metric photogrammetry that measures the precise measurement and computational to determine the shape, size of the object. The branches are analog photogrammetry, analytical photogrammetry, and digital photogrammetry when you talk about satellite photogrammetry. So for creation of this photogrammetry, you will be requiring a stereo pair in image that involves an overlap area. Then you will be requiring the software which can process the stereoscopic data sets. Then you will be requiring the ground control points to register the image into the ground for geometric corrections. And the basic definitions that when you're using for photogrammetrical observation, some basic instruments and the basic terms are the stereo pair. So what does the stereo pair means? That is the pair of photo or images having common overlap area, that is your stereo pair. Then you have got and lapping along the flight strip, that is 55 to 65%. Then you have got side lap, that is known as lateral overlapping between the two adjacent strip, that is 20 to 30%. Then you have got flying height, that says altitude of the camera. Then you have got a strip of the photos, that is the photographs of two or more and lapping pairs. Then you have got block of photos, that means the photographs of two or more side lapping strips. Then you have got exposure station, that says the position of the camera at the time of exposure. Then you have got perspective center, that says about the point of origin or the termination of a bundle of perspective rays. Then you have got fiducial marks, the marks that are exposed on the negative when the picture is taken. So these are few of the terms that you're being using when you talk about the along track cameras or a scanner, or when you talk about the across track cameras and sensors. So you can see how the methods of obtaining those methods points. So these are the fiducial lines, and that are used for different kinds of calculation of principal point, that is the foot of the perpendicular from the perspective center. Then scale represents the photo distance to the ground distance. Then you have got a parallax that suggests the difference in the vertical direction of the image of the object, that is improper orientation, tilt of the photos, variation in the flying eye. Then you have got a stereoscopic parallax that says about the change in position of an image of the object from one photo to next photo caused by the aircraft motion, and that is your ax parallax. Then you have got relief displacement, which suggests about the shift or displacement in the photographical position of an image caused by the relief of the object. Then this is the various kinds of a truly vertical optical axis. Then you have got tilts. Yeah, then you have got low oblique photograph, high oblique photograph, vertical photograph, that we have already covered major of the portion in our earlier semester. So I'll be not going into the deep about the histographic depth perception, that we have already completed. Parallax computation, this is a kind of a revision that we are doing of our earlier topics that we have completed in our first semester. So if a nearly object is observed alternately with the left and right eye, its location will appear to be shift from one position to the another. This apparent displacement caused by the change in the point of the observation is called as a parallax. So the parallax is computed from the algebraic difference of p of two position along the scan lines. So some of the processings that we have to do for photogrammetry is interior orientation, resection, image matching, space intersection, interpolation, digital Alician model creation, ortho image generation, and then after we'll be validating the data sets. So when you talk about interior orientation, we are talking about reconstruction of the geometry of the bundle of rays from the perspective center of the object space. When we talk about exterior orientation, we define the attitude of the camera both in position wise and the orientation wise with the reference to the terrain space coordinate systems. Then you have got relative orientation, where orientation of one photo with respect to another or orientation of both with respect to the third system is generated. Then the input image corresponds to the image coordinates, IO parameters. Output corresponds to the arbitrary model coordinate system. Principle used is polarity condition. Then you have got epipolar image that denotes about the stereo players that are reprojected so that left and right images have a common orientation and the matching figures between the image appears along a common axis. Then the space intersection is used to compute image and object coordinate systems. Principle used is collineatory condition applications to get model coordinates, bundle block adjustment. Then you've got absolute orientation, where the orientating model with respect to ground transformation from the space to the ground surface. Then you've got principle that is based on 3D conformal transformation. Then unknown coordinations, step formations. Then bundle adjustments will be doing in bundle adjustments will be taking simultaneously exterior orientation of n photographs covering a block, and this is used to achieve the best possible interaction of all conjugate rays in their true orientation to shoot a given ground control. The input is observed and refined photo coordinates of GCP and try points and pass points of all photos. GCP coordinates as provides on the ground and post pointed in all photos. Outputs is 6 EO parameters for each photo, 3 ground coordinates of each tie and pass points. These are how you will be providing the photo blocks, and finally you will be creating a digital elevation model and an orthophoto image, where a photograph or image showing the image and of object in a true orthographic position. The orthophotos are therefore geometrically equivalent to the conventional line and the symbol planimetry maps, which also show true orthographic positions of the object. Orthophotos are generated from perspective photos using differential rectification, which eliminates image displacements due to photographical tilt and the relief. So some of the physical sensor model over generalized model says in general the rigorous sensor model of an image is used for transformation between the 3D object space and 2D object space. It includes the physical parameters about the camera such as focal length, principal point location, pixel size, lens distortion, and orientation parameters of the image such as position and attitude. Since satellite imagery consists of both parallels as well as perspective projection, each image scan line is taken at a different instance of a time. The exterior orientation parameters like attitude angles, roll, pitch, yaw, state vectors of the perspective sensor changes from one scan line to the another scan line. The rational function model is a general version of the polynomial model that describes more complex image to ground transformation. It is otherwise called as rotational or rational polynomial coefficient model that is used for an alternative solution for the rigorous physical sensor model. The RPC models form the coordinates of an image point as the ratio of the cubic polynomials in the coordinates of the world or object space or on the ground point. It is also a set of image that is given to determine the set of polynomial coefficients in the RPC model to minimize the error. Then rational polynomial camera model is used to represent the imaging geometry of cartosat 1. It is expressed as the ratio of two cubic polynomials which are the functions of ground object. It is one of the important products realized in cartosat 1. Cartosat 1 AutoKit products are already in demand among the various global users which are able to perform the required geometric processing including DEM generation, ortho rectification at the and with the help of standard quartz package. So these are the various elements that we are talking about when you talk about cartosat 1. The launch date is 5th May 2005. Mission is for stereo observation of the Earth surface, terrain modeling, and large scale mapping. Altitude is at 618 kilometer. Two high resolution imaging cameras. 4 is at plus 20 degree and after is minus 5 degree. Near simultaneously imaging of the same scheme with a delay of 52 seconds between the 4 and the after acquisition. The spatial resolution is 2.5 meters on the ground. Along track stereo data collection with 30 kilometer swath with a base height of 0.62. So this is how the satellite data is taken. This is when it is taken for the forward stereo acquisition, and this is taken when the reverse stereo acquisition is taken. So this is the 4, this is the after. In the reverse it will be just vice versa. So for Sar Interferometry, when you talk, this was the satellite photogrammetry based observation. Now we'll be going for the Sar Interferometry. Then the Sar Interferometry is a spin of active microwave remote sensing, in particular synthetic aperture radar technique. Here the phase value of two complex SAR seen of the same location will be interfered to generate interferograph fringes. These fringes are related to the elevation of the terrain. So they are the different methods through which we'll be generating the digital elevation model. In INSAR is a nested acronyms. It stands for interferometric SAR. SAR is an acronym for synthetic aperture radar. Radar stands for radio detection and ranging. D-INSAR stands for differential INSAR. Interferometry is the study of interference pattern created by combination of two sets of radar signals. INSAR makes use of phase difference measurements determined or derived from two satellite image which were acquired. So these are the various bands with their frequency that we are using in microwave satellites. So when you're talking about the P band, the wavelength is from 136 to 77 centimeter, frequency is 220 to 390 megahertz. So this we have already done in our earlier exercises, so I'll be not going into the detail. When you talk about wavelength, the wavelength is the distance traveled through a single cycle. Then you have got a phase, that is the wave of the total number of cycles of a wave at a, that is the frequency. Then amplitude, we have already done, that is the displacement of wave at the peak, then coherent source. So this all we have already completed in our first semester exercises. The polarization also we have done. So polarization is defined as the direction of orientation in which the radar transmits and receives the electrical field vectors. There are four possible combination, that is HH, HV, VV, VH. Then circular polarization is RH, RV. Like polarization is radar sends and receives the waves in the same direction, that is HH and VV. And cross polarization means radar sends and receives the waves in the orthogonal direction, that is HV or VH. Then these are the various radar geometry that we have already done in our earlier exercises. So this is a kind of revision. By seeing this photographs, you can revise all the topics that we have already covered in our earlier exercises related to Sar Interferometry, where the Sar system illuminates the earth with a beam of coherent microwave radiation which retains about the amplitude and the phase information in the radar echo during data acquisition and subsequent processing. The Sar Interferometry exploit coherence using the phase measurement to interfere differential range and the range delay in the two or more complex valued Sar images of the same surface, thereby deriving more information about an object that is obtainable with one single image. The resulting difference of phase is a kind of new image which is called an interferogram, which is a pattern of range containing all of the information on relative geometry. So that's why I'm going into some speed, because we have already completed this all exercises. So you can see this is the repeat pass. So the steps when you are going for SAR interferometry, score resistance of image at pixels and subpixels level, then generation and filtering of interferogram, subtraction of light, odd phase interferogram, enhancement, coherence calculation, phase unwrapping, generation of digital elevation models, and geocoding is performed. Thereafter, we'll be doing the code registration, where we'll be aligning of master and slave image, then codes registration, matching image on the pixel level, and file code registration, where sub-pixel alignment of the image. Large variety of techniques will be used for pixel code registration. Then you have got interfograph generation. Then you have got, will be generating this all generation, and you will be seeing the product. So this is how it is done. So hello.
Yes, sir.
Yeah. So today I'll be stopping up till this radar photogrammetry and satellite photogrammetry. Next, in tomorrow's class, we'll be doing the rest of the topics where I have left today. So this is for today's exercise. In case there is any confusion, we'll be discussing it right now with your quiz in your LMS.